Okay, good morning. Thank you for joining this session for your first session of today. My name is Wirth. I'm from Oracle Labs. I'm based in Austria. And I'm presenting you today our engine, our Graal.JS engine, which is a JavaScript engine for the Java virtual machine, where you can execute JavaScript programs with very high performance. We are fully standard compliant, and I will show you how we do that and what else you can do on that engine. So I'm not only going to talk about JavaScript today, I'm also talking about Java. I'm talking about language interoperability. How can you integrate other language engines like Ruby, Python, Erlang, C, Clojure, or whatever language you want to add to that list. I'm from Oracle Labs, which requires that I show you that slide, which basically means all we do is research. None of what we are doing will ever be a product. Of course, we hope that it will be a product, but I cannot promise you. So what am I going to talk about? The first thing I want to show you is what is Graal and what is the GraalVM. What can you use that for? Then I will tell you how did we implement this Graal.JS engine? How can we make JavaScript really fast as all the other engines on the JVM? Whenever you talk about JavaScript, you need to talk about Node.js. So I'm going to show you how can we execute Node.js on our engine and how do we test that we really fulfill all the specifications and all the tests and all the compatibilities to existing engines. And finally, that's probably the most interesting talk for you, unless you're a JavaScript developer, is language interoperability. How does our engine hopefully solve the problem of language integration, of language interoperability? How can you write programs in multiple programming languages? Now, to start with GraalVM. What is Graal? What is this Graal virtual machine? The project I'm in started off as a Java on Java compiler. So what we are talking about is a just-in-time compiler for Java written in Java. As you know, the current Oracle virtual machine, the hotspot VM, has two compilers, the client compiler and the server compiler. Both are written in C++. And we think in the future we want those compilers to be written in Java. They might be easier maintainable, they might be easier to do research on, it might be easier to extend them, to write new optimizations, to write new features, to extend Java in the future. That's what we have written Graal for, so Graal is a just-in-time compiler. I guess most of you know what that is. Just to get the picture clear, I'm not talking about the compiler that translates Java to bytecodes, but the software artifact on your machine that at runtime translates Java bytecodes into machine code. So you get really high performance, basically native performance once it's compiled. GraalVM now is basically the existing hotspot virtual machine with Graal used as a compiler. We're still using the existing compilers, server compiler and client compiler, to compile Graal itself, as Graal is a Java program. But the application that you execute on top of this GraalVM is then executed by Graal. What we've done is, in the first instance, a Java compiler. But we thought, how can we extend that? How can we add more to this environment? And everything that Graal does is optimized for more than just Graal. We try to compile other languages with high performance as well. I've added some here on the list that are done internally in Oracle Labs, JavaScript, C, Ruby, and R, statistical language. But more languages are done by cooperation partners, by universities worldwide, or by open source projects. Graal, the Java compiler, is open source. So you can download it from OpenJDK. You can build it yourself. We also have a binary available, I will show you. But everything we do there is open source. You can download it, you can change it, you can do your research, and you can write your language on it. Many of the language implementations besides Java, so for instance, Ruby or R are open source as well. They are also researched in-house in Oracle, but they are open source, you can download them, you can compile them. JavaScript, what I'm talking about, is currently still closed source. But we have a binary release available. We just uploaded it 2 weeks ago for Java 1. And it has the Java compiler, it has the JavaScript engine, so Graal.JS, it has Ruby and R. And all those languages can interact on that engine. That's a very high-level overview of what we are doing to execute more than just Java. On the base layer, you have the operating system, and on top of that operating system, you have your virtual machine, which is the hotspot virtual machine, or a GraalVM in our case. This contains a very small layer which we call Truffle, the Truffle API, which helps you implementing your language engine with very little effort, actually. On top of that is your language engine, so Graal.js is just one example of those engines. And finally, on the very top layer, you have your application program, any JavaScript application, a Node.js application, or an application written in many languages. As you see, most of this stack is implemented in Java. So the GraalVM has a very tiny layer of C++ that you need to start hotspot, that you need to do some memory management, but the core of Graal itself, all the compilation queue, all the compilation itself, all the optimizations, they are written in Java. What's the status of this project? How far are we as we're doing research? We are pretty far already. We support everything that's in the Java spec. So just about any Java program that is out there, you should be able to run with Graal. If you find any bug, please tell us. But we think that we are there and we can execute all the programs. As I said, this is open source. You can download it. You can compile it yourself. Now the question is, we are in hotspot and we need to modify hotspot. So what does that mean for you? How can your customers use Graal? And the good answer is, the good news is, there is the GEP 243 Java enhancement process, and that's how is it called? Java level JVM compiler interface. We call it JVM CI, Java Virtual Machine Compiler Interface. That will be in JDK 9. At least that's the current plans. It's almost done. It's ready to be included in JDK 9. So that will mean Graal itself won't be in JDK 9 most likely, but this interface will be in there, which basically means you can drop in Graal or any other compiler adhering to that interface to any existing hotspot virtual machine then, starting with JDK 9. So in the future, you're more free to select what compiler you want to use in your hotspot virtual machine. So much to Java. Now let's go to Graal. Let's go to Graal.js. Let's go to JavaScript. This is our engine, and it's basically Oracle Labs showcase tool, our main example for this Truffle API and for more than just Java on the JVM. It's developed in-house at Oracle Labs. It's closed source, as I said. We're working on open sourcing it. Might take some time because we need corporate approval for that, but we hope we can do that in the future. We support 100% of the previous ECMAScript 5 standard. Now this summer ECMAScript 6 came out, or ECMAScript 2015 as it's now called. We implemented all the features already, so everything is there. We're not fully compliant to the standard yet, so the official test suite says like 99.5%. I hope we're gonna finish that this year, so then we are really standard compliant. That score should actually be higher than many of the other engines. So V8, for instance, Google Chrome's compiler has less than that score. Whenever you talk about JavaScript today, you're gonna talk about Node.js as well, because we think that JavaScript, when you execute it on the server, most people are gonna use Node.js. And I want to make that clear, we're not talking about JavaScript in the browser. That's not what this project is about. There are many good engines out there that can do that already. We really concentrate on everything that's on the server for longer running programs, for data-heavy programs, for programs interacting with other languages, with Java, with a database, whatever. two parts, and just to drop the names here, which we use in Graal.JS, is the truffle API. I will show you in a minute what that means. That helps you to implement your an abstract syntax tree interpreter for your language. And the second thing is the polyglot engine, which we use for language interaction. Now, the amazing thing is we wrote a whole new JavaScript engine. Other people did that before, but if you take, for instance, Google's V8 engine, they had to write everything from scratch. They wrote their memory management from scratch, they wrote their garbage collector from scratch, all the library support, whatever they do, they had to rewrite. That's not true in our case. We already have a working VM there. We already have GraalVM based on Hotspot VM, so we can reuse all those components. And our job was not to implement everything from scratch, but to take what is there and try to see what's the minimal thing that you need to do to have a fully compliant language implementation. So our approach is to write an AST interpreter, abstract syntax tree interpreter. That's one of the easiest ways how you can implement a language engine, to interpret that language. That's very easy to code. Every student in our university learns that in grad school, so there shouldn't be any major issue with that. Of course, the problem is, and I see you thinking that in your brain, interpreters are slow. I will show you how we solve that issue. Now, as interpreters are easy to code, our effort was really, really small. So to get the fully standard compliant ECMAScript 2015 engine, it's about 80,000 lines of code, 80,000 lines of Java code. A few lines of JavaScript code because we added some of the advanced features of ECMAScript 2015 in JavaScript. So I think that's a reasonable amount of effort to implement a language engine. That's something that a small team can do in 2 years maybe. Of course, we have some external dependencies. We depend on Nalson, which is another JavaScript compiler by Oracle. For parsing, we depend on the Joni library for regular expressions, and we depend on Avatar.js for Node compliance. We are writing a new engine for something that already exists. JavaScript engines are out there, and people are using JavaScript. People have already written JavaScript applications. So what do we need to be compatible to when we want to enter that market? Of course, there is the ECMAScript standard, which is a very nice written standard, defines almost all aspects of the language. And as I have shown you before, we are very compatible to it. Few edges to cut off, but we're almost there. On the other side, there are existing engines. And that's a bigger problem, because those engines don't always adhere to the standard. Google V8 and SpiderMonkey, and take all the other languages that are out there from Apple, from Microsoft, whatever, they add their own features. And that makes it very complex for a language implementer to figure out what do we really need to support to get your program running. The third here on the picture is Node.js. Node.js adds another layer of complexity. Node.js has its own base system implemented in C++, it adds JavaScript code, it adds new APIs, new layers that you need to be compatible to. And talking about Node.js, you can implement modules in Node.js not only in JavaScript, but also in C++. And here's where the real trouble starts. Implementing a module in C++ means you implement it against the V8 API. And that one is changing with every release of V8, with every release of Node. Now people are going to work on that. There is the native abstractions module in Node.js currently. They try to tackle this problem, to abstract it, and to make it easier to keep compatible with new versions of JavaScript, with new versions of V8 and Node. But currently we have to support the internal API of that Node version that we want to support. Taking V8 now as an example, what are the difficulties there? We have the standard, but why are those engines different? The V8 engine, as most engines, add their own extensions, and I listed just a few here. You have a stack trace API, you have more global symbols that you can use. They have fields on the regular expression function. They have the strong mode, which is a very nice thing in the future. But all that stuff adds to complexity. And it's not really well defined how to implement that. On the other hand, all those features are used by code out there, and we think it's reasonable to do that. So this is stuff that we, to some extent, do not support currently, but we will in the future. We think it's very important that that is in there. That's the one side. The other side, which we don't like so much, is off-spec behavior. And that's where V8 or where other engines clearly violate the specification of ECMAScript. I listed just a few here. For us now in ECMAScript 2015, the most important one are proxies. The V8 implementation is totally off-spec on proxies. It has different traps. It has a different way to create a proxy. In the standard, you would need to call the constructor. V8 calls a factory method. Now, we can support that in the future, but we still hope that V8 comes to senses and supports that as it's defined in the standard in the future. They have some open issues in their bug tracker on that, but they seem to be a bit resilient currently, but let's see what the future brings. But also other behavior where we see, oh, our engine is failing the tests of V8. Why are we failing them? Because the test itself is wrong from our point of view. So that leads to us not passing all V8's tests, and we try to figure out what tests do we really want to pass, what is relevant for us and what is relevant for use of our engine that we pass. So from the 2,500 tests that are currently in the test suite, we consider only 2,170 about to be relevant. Those are the tests that we want to pass at one point in the future. And currently we only pass 87% of that because we're missing some of the extensions that V8 brings. But that doesn't mean that a program that you download from the internet doesn't work. Usually most programs will work because all those features are not used widely. They are used, but not by each and every program. Now, performance. I'm talking about a JavaScript interpreter written on Java, which itself is an interpreted language. Isn't that horribly slow when you execute your application on that? I'm going to show you some numbers, how fast we are on peak performance. I want to put a big disclaimer there. Whoever of you has ever done benchmarking knows how hard it is to really benchmark and figure out what do you really want to know, what do you want to benchmark, which heap do you want to use, which application do you want to benchmark. We have selected the V8 Octane suite, so the suite from Google's V8 project, and we executed it on our benchmark server. We do that regularly, basically for every push that we do to the server. And those are the numbers. I compare Graal.JS against V8 and SpiderMonkey here. And the takeaway message here is that for the benchmarks I show you here, we are basically the same performance as V8. Sometimes we are a bit faster, sometimes, or on many benchmarks, V8 is a bit faster, but it shows you that we are in the same ballpark as V8. It's not that we are factor 2, a factor 5, a factor 10 slower. We are maybe a factor 10, we're 10% slower on some benchmarks. We're 20% slower on some benchmarks. We're 20% faster on others. So you see, with reasonably small engineering effort, I'm talking about 80,000 lines of code here, we can write a JavaScript engine that's fully standard compliant and that can execute code with very good peak performance. How do we do that? I told you before that we are talking about an abstract syntax tree interpreter. What is an abstract syntax tree interpreter? It basically means when you start with some code like a plus b multiplied by c, you create a tree of nodes here. You have a multiplication node that has a child c, which can be a variable read node. It can also be a constant node, depending on what c actually is. On the other side, you have an add node, which adds a and b. Same story here. Now, what does the add node do? It has an execute method. Every node in our tree has an execute method. And this node reads the value from its A child, from its left child, and from its right child. Both those nodes return a value, which is an object in this case. And then it calls the add method, which what I show you here is not JavaScript semantics, it's an abbreviated version, but just to get the picture, if both values that we read are integers, then add them with integer add semantics on Java. If both values are strings, then concatenate those strings, and in all other cases, well, go to some generic method that does the magic. Of course, that will be horribly slow when you execute it in your code. Because every time you execute that, you have to figure out what are my values, what types do I have. You have to box them if they are numbers, because you're using objects here. How can we get that fast? The interesting observation here is JavaScript is a dynamic language. You can use different types, you can mix types, you don't have to define them at compile time. But at runtime, statistics have shown, research have shown, even in 1970s, that at specific places in your program, there is a very high chance that types do not change. If you observe an integer at one position in your program, it will stay an integer. Maybe it will deviate to a double, but it will never be a string, most likely. And we can use that in the sense that when we execute the program for the first time in our profiler, in the interpreter, we figure out, do we use an integer, do we use a string, do we use something else? And then we rewrite our node, we replace the node in the tree. So we can make an integer node out of that does just the thing we wanted to do, adding two integers. Or we replace it with a string node that does just concatenate two strings. Or we go to another third case, which is more generic. So starting with the tree here on this side, we specialize all the nodes in this tree depending on what data, what values we see at runtime. I've shown you here how we specialize, or how we could specialize in an easy case on data types. So we only get more generic. From integer we can go to double, but we can never go from integer to string or vice versa. In that case, if that happened, we go to the generic case. That way we specialize our tree. This is not only done for data types. You can do that for any optimization you can think of. For instance, we do it for object accesses, whether we have to create that field on the object. As JavaScript is a prototypical language, you don't have classes, you need to change the classes that you see. Or whether we write to an object that already has that field, where the writing is much simpler. We do the same for arrays. We specialize on how we store values in arrays. JavaScript basically defines that there is a hash table, a dictionary. But of course, when we see that this dictionary only has the indices 0, 1, 2, 3 written with integers, then we will use a flat Java integer array to store the values. And we use this specialization strategy to optimize the writing and the reading access to that arrays, so that the performance will be as if you had written in Java in the first place with types. After some time, this tree will have all the values specialized. All the nodes will be specialized. In this example here, you see we have 3 nodes that specialize on integers, 2 nodes that specialize on generic. Now, here comes the real magic. We take this tree and we compile it. And before we compile it, we perform what's called partial evaluation. The simplest description for partial evaluation is we take the whole tree and we inline all the execute methods into one huge function. To do that, we need to assume that all the call sites are stable, so that all the child nodes are stable. But if that assumption holds, we can really create one method, one compilation block that we compile and where we generate machine code for. And this, in the end, results in the hopefully smallest possible Java program that executes your JavaScript application. So if you had written the same thing just for that input JavaScript program, you wouldn't have been able to write a better Java compiler. This gives us machine code, and machine code should be pretty fast. Of course, during execution it can happen that data types change. Arrays can grow, objects can have their values deleted, we can overflow an integer value, or the user can suddenly input a string where only integers are expected. Here the Java virtual machine helps us a lot. In that case we can de-optimize, so we can throw away the compiled code. We go back to interpreter. The interpreter can execute all programs because it's not specialized. We can rewrite our nodes. So in that case we rewrite from an integer node to a double node. And then again, after some time, the program can be recompiled and it can again execute the program as fast as it would be possible with that data that you have as input. So much to our core engine. Now let's look into Node.js. And here the good news for us is we didn't have to implement much, because there is an avatar project, or there was an avatar project at Oracle, where in the avatar.js code, in the avatar.js project, they tried to execute JavaScript programs on top of their stack and to make them execute Node.js code as well. We could just take their recast, which basically is taking all the Node core implemented in C++ and rewriting it in Java. We took that code, and that was almost everything that we had to do to execute Node applications. Now, the question is that enough? Can we execute all Node applications? Because we have no clue whether that means we can execute 35% or 99% or all Node.js applications. How do we know? How would we test that? The NPM project, the Node Package Manager, has more than 200,000 modules. 200,000 modules that we can use to test our implementation. And that's what we did. We took many of those modules. Now here, many of those modules are implemented in JavaScript. Some are implemented in C++. We're working on the C++ support, but currently we cannot really support that. It's a very tiny fraction of modules that use the C++ implementation, because when you're using Node.js, you want to use as much JavaScript as possible. But the tiny fraction has some very important modules for us. We are Oracle, we want to support the Node Oracle DB driver. Couldn't tell my manager that I cannot execute that. So in the future, we will have to support that. We're working on that. But for what I'm going to tell you now, we're just taking a look at JavaScript modules, at modules that are implemented in JavaScript. How do we do automated testing on them? How do we test those 200,000 modules, whether we can execute them? There is the good news that most of those modules have a test command. So we can execute test on the module, and the module will tell us whether it's fine or not on our engine. The bad news on the other side is that this is totally unstructured. There is no well-defined way how a test reports whether it's passed or not. It can just write any message, it can have a return code, it can crash, it can print fail, it can print pass, it can do whatever it wants. So our approach here was, for now, to get a first feeling, we took the 30 most popular modules. And by most popular, we mean those modules that were referenced by other modules the most time. And we made them work. So we figured out what do we really need to know to see whether this module has passed the tests or not. And that's what we are currently testing. We are passing, you see this value is around a month old. We are not passing all the tests. There are many, many reasons for that. Our recast is not perfect. We need to change in the recast. Some of those fails come from what I told you before. We're not fully ECMAScript 2015 compatible yet. We're not fully V8 compatible yet. We have some crashes in the compiler even, but it's very nice to have that huge set of tests. If any of you knows of a better strategy to test Node.js modules, or if any of you wants to work on fixing a problem in NPM, I would be very happy to hear from you. But right now we try to automate as much as possible, but unfortunately NPM doesn't give us so much here. Now let's come to the last part of my presentation, which is about language interoperability. I told you about JavaScript that can be executed on a Java virtual machine. Of course, there is a way to interact with Java, but there can be more. The promise given by the Java virtual machine initially, and also by other similar things like Microsoft's Common Language Runtime was, yeah, you can execute all languages on our engine. Is that true? Well, it is to some extent. You can execute all programs, all programming languages on the Java virtual machine, but we would like to add to that sentence, as long as it looks like Java, or as long as it looks like C#. Because when you execute something on the Java virtual machine, you have to translate the program into Java bytecodes. And Java bytecodes are not a great tool, for instance, to implement a functional programming language. It's getting better, but it's not perfect for that. Of course, that might be a controversial statement, but in the end, many languages cannot be fit well to Java bytecodes. So we think there should be a better way. And we think the programmers want to write programs in more than just one language. So when a programmer tries to do that, he has a Ruby program and he wants to call JavaScript. Typically, there is no interface for that. He can simply not do that. Sometimes he has the possibility to do. But if that, then he has to write lots of wrapper code, typically. So when you use JNI, for instance, you have to write more than you just want to write. It's not as easy as it should be. And besides not being as easy, it's very, very slow. So every time you cross the boundary between two languages, you're in a whole new world. Everything has to be reset. All assumptions have to be taken new. Just a small example, what we want to do. Assume you have a C program where you use a complex data type, and you have a JavaScript function, JavaScript method, that does the add for this complex, for two complex values. There is no way currently you could execute the JavaScript function from your C code. That's a very small example, but consider you have large applications where you want to do something like that. It's simply not possible, or not easily possible, or it will be slow. But we think programmers want to do that. Programmers want to reuse code. Programmers want to use the most suitable language they know to solve a problem, and not just the one language that the project started in. And on the GraalVM, we allow you to do that. We allow you to use more than just one language. You can gradually migrate projects. You can take two existing code bases of different languages and let them interact without writing much boilerplate code. I hope I have time and it looks good. I can show you a demo what we really need to do to let that interaction happen. And very importantly for us, when you reuse existing code, we don't want to have a language boundary. We don't want that to be horribly slow. We want to be that as fast as if you had written it in just one language in the first place. Now, is that possible? What do we need to do that you can have languages interact? Assume the GraalVM again. With a JavaScript program, you see the code here. We read the value field of an object, and that's JavaScript code. So all the tree currently is JavaScript. But as we're in a multi-language environment, assume that the value that flows in, so the object itself, the value stored in object, is not JavaScript. It is, in fact, a C structure. And we want to read the value field from that structure. Cannot do that currently. But we can do it, because when we figure out that this is a C structure, we replace the JavaScript specific object access that reads object and value and returns the value field from object with a read message. The read message is totally language independent, and it just knows read me value from object. Of course, this read message doesn't know how to solve the problem in the end. But as there is a C value in our system, there needs to be a C interpreter somewhere. A truffle-based C interpreter must be in our engine, otherwise we wouldn't read a C value. So the read message can just go to that C interpreter and ask, hey C, how do you read value from object? And C, of course, needs to know the answer to that. It cannot only read the value, it can do, in our case, something even better. It can tell us how we can do that. So it can provide an AST snippet. It can provide a few nodes that know how to read value from object if it's a C structure. And we add that code into our JavaScript program. Now, in the end, all this is a Java program. So it's not a problem that we mix languages here. It's not a semantical problem, not in our engine and not for JavaScript, not for C, because in the end, this subtree here will return a value of type object. So the JavaScript node here, the assignment operator, can use that object, no problem. We can do that, and it will work very nicely. What we also add here is a check whether it really still is a C value. Again, we can partially evaluate that. We can compile it to machine code, which will result in a machine code that is comprised of different languages. In our machine code, we have now mostly a JavaScript engine, but some parts are from C. And this also works when you have more than just one or more than just two languages. When we add Ruby to the game, we just create a polymorphic inline cache where we ask, oh, is this C? Then do this or that. If not, it's Ruby, then do this or that. And again, you get the best performance even if types of different engines are flowing through your program. How fast is that? Same question as before. What we did here is we took benchmarks from the language shootout game benchmarks. And they are implemented in different languages. They are implemented in JavaScript, in C, and in Ruby. For all three, we have an engine, so we benchmark the execution. And that's the result. We have one outlier here for the towers, where the C engine is not as fast as it should be. The values are normalized to the C engine, and not unexpectedly, the C engine is usually the fastest because object accesses are simplest in C. JavaScript engine, on the very left you see the composite score. It has about a performance of 60% of C. And the Ruby engine, again, is a bit slower, about 30% of C performance. Now, what did we do to really test our multi-language runtime? On the next slide, what I will show you is we still take only the JavaScript implementation. So you will see 3 bars for each benchmark, and each one of them shows JavaScript engine. The code that we run is JavaScript. But we replace the allocations so that you not only see JavaScript engine executing JavaScript objects, but also the JavaScript engine executing C objects and Ruby objects. And that should be slower than the JavaScript engine. But it's not. The black bar here is the JavaScript engine operating on JavaScript objects. That's what you usually do. But amazingly, the JavaScript engine executing on C objects, on C structures, which is the red bar here, is actually faster. Your program is executed faster when you change your objects from JavaScript objects to C objects. And for us, that is proof that this is a very useful technology. You can mix languages, you can execute applications in combined style, you can exchange data between languages in your application, and you won't lose performance. In some cases, you will even gain performance. Of course, if you let Ruby objects flow through your engine, performance gets slower, but it's still working, and that's the very good news here. Now, before I come to the conclusion, I want to prove that this is working, and I'm trying to make a demo. Let's see if everything is working as expected. This is our shell. It's a multi-language shell. I hope not as sharp. Let's make it. I hope you can read it. It's, yeah, should work. This is our multi-language shell, and you can switch between languages here. Now it's set to R, but I can go to Ruby, to simple language, our example language, to JavaScript or Node.js. I'm in R, and let's set a value to a vector. This now sets 100 million elements to this vector, 100 million random elements. So length of V should be 100 million. And the sum of V is about 50 million, of course. So how long does it take to calculate the sum? We have a time function of sum V. It's pretty fast. It's less than a second, significantly less than a second. Of course, we can also implement the same thing, so the sum in R itself, and that will be slower. If we execute it, it will take about 4 seconds. I'm doing the whole thing here in VirtualBox, which is not a good thing to do when you do benchmarks, but just for the demo, it should be fine. Now, if I execute it several times, it will take about 6 or 7 times here now, our compiler will kick in, because currently all this is executed in the interpreter, so it's slow. It's like a Java interpreter in the beginning, but once this is compiled, it should be faster. It won't be as fast as the built-in sum function, but it should be really, really close. Now, yes, you see, it's at this try, it's twice as, so it takes twice the time of the built-in function, but that's okay. Now, I'm gonna have a JavaScript function, so I switch to JavaScript here. This is a JavaScript add. It takes 2 parameters and just adds them and return them. So I can call JS add of 7 and 8, and it should be 15, right? What we also have here is export. Now, this is some kind of boilerplate code, but it's not actually required. We do that because we think we don't want to bloat the global environment. We could do totally without that. We could export all values from JavaScript to all other languages. We think it's more reasonable to not do that, to only export really what the user wants to export and to import what you want to import. But probably if this ever is a product, we're gonna have that behind a flag, so you can really export everything if you really want to. That's not a technical limitation. It's just for us to keep the overview. Now we are back in R. And in R, I have a new function, rsum2, and this one imports our JavaScript add. It then iterates over all the elements. Recall, these are 100 million elements, and for each and every one, for 100 million times, it calls the JavaScript add and sums up the value in the end. So let's benchmark that. Again, it will be slow first. It will probably also take 3.5 seconds. And again, if I compile it, so if I execute it several times, the system is not prepared for a demo. It should compile really, really faster. If I execute it again several times, it will be as fast as before. Sometimes it's even faster because in JavaScript the arithmetics are even a bit faster. Yeah, you see 0.2 seconds. It takes 0.2 seconds to iterate over 100 million elements in the R language, transfer the values to JavaScript, sum them up there, return to R, and calculate the value. I hope this is kind of proof for you that this language interaction really is working and is working as fast as we expect it to be. Now, I told you lots about our engine, about language interoperability. Especially language interoperability is a field where I could have a whole talk of its own, and maybe for each language, a full talk. And this is very new research. We had a PhD student currently working on that at JKU Linz, at Johannes Kepler University in Linz, and we're currently taking over that approach into our engine. So the demo I've given you has been shown for the first time 2 weeks ago at Java 1. We really try to integrate that and make that work for each and every scenario. But there is much more we could talk about. If you're interested, keep listening to our Twitter feeds and to our releases. What we are also working on is parallelization. JavaScript is a single-threaded language, but there are many ideas out there how you can parallelize it. We are also trying to parallelize our executions. We have a software transactional memory approach there, how we automatically parallelize loops, but we have also other ideas how we could give an API to a user to execute code in parallel. On the truffle level, so on the language interaction level, we're working on instrumentation. We think you should be able to instrument each and any program that you have, regardless of what language it's implemented in. As we can share data between languages, that shouldn't be a problem. And based on that, we provide a debugger solution and also analytics tools for your program. So for instance, we're currently working on a debugger that you can debug our applications that are implemented in more than just one language, for instance, in the NetBeans debugger. Being Oracle database has to be everywhere, so we are also working on database optimizations. We have some ideas how you could optimize the database access from Node.js, from JavaScript applications, also from Java. We can use the same system of specialization also there very nicely. If you want to learn more on what we are doing, I told you before, Graal is open source. You can download it, you can compile it yourself, and that's everything you need to implement your own language. If you have one language you want to add to our list, you can do that, make an open source project on it, and please tell us about it. Also, if you just want to use the JavaScript implementation, we have a technology preview released on the Oracle Tech Network. You can download it there, play with it a bit. This language interoperability, as I've shown you, the demo I've given you, should be working there. If it's not, please tell us. We know that this is really research. We still put it out there for you to try out. Tell us what you're interested in, tell us your scenarios, and we will try to make them work and integrate them in future releases. That's all from my side. Thank you for your attention. And if you have any questions, we have 10 minutes left to answer them. I have a hard time seeing you, but are there any questions? Yes?
In your example, you just export one function from JavaScript to R.
Yes.
And is it already possible to do that from Java to JavaScript and in the other route?
Okay, the question is, in my example, I've written a JavaScript a function and exported it and used it in R. Is it possible the other way around, and can I do the same with Java? Honestly, I tried to rewrite the demo, so I start with JavaScript and that didn't work. I just got a crash. But that's what I said, we just integrated that 3 weeks ago. The idea is yes, you should be able to do that from each language to each other language. We can, even better than I've shown you, integrate with Java, but that's not big news now. Someone can do that, or has been able to do that for 2 years now, and Rhino had been able to do that. But between our truffle-based languages, we should be able to export functions, export values from each language to each other language. We're not there yet, or it's not 100% working. At least I wasn't able to make it work, but that's what we want to do. Any more questions? Yes?
The GraalVM, does it target specifically dynamic typed language, or can be useful also for statically typed language?
Does the GraalVM target dynamically typed languages? The answer is yes. But you have seen that C is on our list of supported languages. So initially we thought that dynamic languages are the main target here because we can gain most benefit. JavaScript, Ruby, Python, that are ideal showcases for specialization as we've shown it. But as you have probably seen in the language interaction benchmark, C is fast. C is way faster than our JavaScript examples, and the C implementation that we have is almost as fast as GCC. Not in all cases. GCC is a great product and we have a hard time beating its performance. But we can also work on statically typed languages like C, and we also have a language engine for Clojure and for Erlang. A student is currently working on that. So we try to target more than just dynamically typed languages. But the dynamically typed languages are really the main idea why we did it and where we are best at.
Thank you.
Yeah?
If you don't mind, because I remember a research project for IBM that made the JAX VM, which was a meta-circular VM which targeted with a Java interpreter for interpreting Java code. Is that a possible target for you?
So a Java interpreter that interprets Java code. Yes, you can do that. We even think that that would be quite reasonable to do if you re-implement Java as a truffle-based language, because it would make some things, especially in interaction, way simpler. Right now, Java is always a special case for us because Java is different than all the other languages for us. If we re-implemented Java on top of Truffle as a language interpreter, we have thought about that before. Yes, but it's not totally necessary. But if you find a student that is interested in doing that, might be a great topic. Any more questions? If not, then thank you. I will be around whole day, so if you see me and have more questions, feel free to ask me. Thank you. Bye.